Alright, so here we are back at it. Our next unit deals with Chapter 4, atomic structure. So obviously we know a little bit about atomic structure. I'm sure you're comfortable a little bit about the things that make up the atom.
Rowan, Ethan, Liam, please come to the office immediately.
So we're talking about protons, electrons, neutrons. We now know even more particles that kind of can be part of the atom. But we're going to basically deal with the real basics of the atomic structure. So Chapter 4, atomic structure, moving right along. The first thing we're going to kind of take a look at is the history, the early models of the atom. It's not like everything we know about the atom now, they knew about 50 years ago, 100 years ago, thousands of years ago. And so obviously this has been an ongoing process of, well, what is it? You know, people just kind of contemplating, thinking, what makes up things? How do things work? How are things designed? And so some of our first scientists, and this is just really kind of just that scientist, Democritus. Democritus was a Greek philosopher, and you're talking 2,000 plus years ago. And he was one of the first to suggest the existence of atoms. Didn't necessarily call them atoms, but thought of them as indivisible, indestructible pieces of things. Didn't explain chemical behavior, just I'm sure he was looking around and seeing all these beautiful, probably granite statues, and said, even if I smash that into smaller and smaller pieces, it's still the same thing. So is there a limit? Can I continually smash it until it's still ridiculously small powder form, but it's still made up of the same thing? So that's kind of where Democritus started us. The next was Dalton, and John Dalton was an Englishman. Notice the year. I mean, we're talking now only a little over 100 years ago, 150 years ago or so, talking about how he really kind of was one of our forerunners of the periodic table. And what he studied was ratios in which elements combine. So that's when you're starting to talk about how, well, if we could look at how H2O has both a hydrogen and of course two of them and one oxygen. So you needed those two hydrogens to get together with the one oxygen and form a compound. So there's John Dalton, and he did a few other things, and certainly we would mention, he mentioned that all elements were composed of tiny indivisible particles, very similar to what Democritus said thousands of years before, but again described them as atoms. Secondly, that all atoms of the same element are identical. So small, like I was talking about, these granite structures or whatnot, whether it's even an atom. Carbon. One carbon atom is the same as every carbon atom, yet different than any other atom. So carbon is different than iron, which is different than oxygen, etc., etc., etc. And that's why when we talk about protons, protons describe what the atomic number is, how many protons it is, which describes what the atom is. So obviously, the number of protons, if they differ, then you have a different element. Lastly, Dalton also, I shouldn't say lastly on this page, described how atoms of different elements can physically mix together to form compounds. And they do that in simple whole number ratios, as you just saw, that 2 to 1, 2 hydrogens, 1 oxygen forming water. So if I move along, just that lastly, also very important when you're talking about Dalton. Dalton said that chemical reactions occur when atoms are separated, joined, or rearranged. And atoms of one element, however, are never changed into atoms of another. And this is groundbreaking when you talk about how the carbon, you know, if we burn something, if we burn a piece of wood, obviously there's going to be some chemical reaction taking place, a chemical change. But carbon, if there's carbon in wood, which of course there is, it's a living substance, that carbon would change to something else, let's say, a new substance, but it's still carbon. So you don't change the elements, okay? I do want to mention a little bit about size. If you talk about atomic size, and thinking about how small. So Dalton's kind of groundbreaking in terms of talking about what's going on at the ridiculously small level. Think about how small an atom is. A pure copper coin, so just a small little coin of a penny, has 2.4 times 10 to the 22nd atoms. And the Earth's population is only about 6 times 10 to the 9th people. Look at this number again here. We talked about scientific notation. 2, 4, okay, 2.4. So we're moving at 22 places. Because it's a positive number, that means it's going to be greater than 1. So 1, 2, 3, 22 times 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 22. We're moving it over ridiculously large versus, the Earth. 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. Nothing even close to how it, and that's the size of a penny, has that many atoms in it. Ridiculously small. So I'm going to get into the structure, kind of a little bit more other scientists in the next little section, but that's kind of the beginning part of what we're talking about.